2:14 in the morning, the first tanker of the day clears the Hilmar Cheese Company receiving dock in Stanislaus County, California. The driver has been on the road since midnight. The tank holds 6,500 gallons of milk, collected from 2 dairy farms in Merced County, the nearest of them 18 miles from the plant gate. The milk left cows less than 3 hours ago. Its temperature at the farm bulk tank registered 37 degrees Fahrenheit. The plant's receiving sensor confirms it arrived at 38. The computer logs the time, the temperature, the originating farms, the tanker identification number, and the sample number assigned to the laboratory queue running in the building to the left of the dock. By the time this driver clears the dock and starts the return route toward Merced County, the milk in his tank will have entered the pasteurization sequence. Hilmar Cheese Company processes over 3 million gallons of milk daily, approximately 25 million pounds, from approximately 400 dairy farms within a 100-mile radius of this single facility in the San Joaquin Valley. The plant produces over 1 million pounds of cheese and whey protein products each day through continuous processing operations that run without pause across all 24 hours. It is the largest single-site cheese manufacturing facility in California. The 3 million gallon figure does not fully communicate what it represents until it is broken into its operational components. 3 million gallons daily means 125,000 gallons per hour. It means roughly 18 to 23 full tanker loads arriving at the receiving dock every hour around the clock. It means 400 farms operating on collection schedules that keep the supply chain continuous. It means a quality testing laboratory processing hundreds of samples each shift. And it means a processing floor where cheese-making vats, whey protein extraction equipment, and packaging lines run simultaneously without the interruptions that would cause milk to back up at the receiving dock faster than the plant can process it. The system that converts those 3 million gallons into 1 million pounds of cheese and protein products daily is the subject of what follows. The San Joaquin Valley's concentration of dairy production that feeds Hilmar's daily intake is one of the most productive agricultural arrangements in the American food system. The valley's flat, irrigated landscape, moderate winters, and access to feed ingredients, alfalfa hay from the Sacramento Delta and the Imperial Valley, a grain from the Central Valley's irrigated cropland and the broader commodity system, made it the destination for California dairy expansion across the second half of the 20th century. Dairies that once dotted the coastal hills around Los Angeles and San Diego relocated east and south to escape urban development pressure and access the land base that larger operations require. The counties of Merced, Stanislaus, Tulare, and Kings developed dairy farm densities that concentrated milk production within distances manageable for large processing plants. A dairy farm within Hilmar's 100-mile supply radius today typically milks between 1,500 and 8,000 cows using freestall barn housing, large open-sided structures where cows move freely between resting stalls and feed lanes, and rotary or parallel milking parlors running 2 or 3 milking shifts daily. A 3,000 cow operation producing 75 pounds of milk per cow per day generates 225,000 pounds, approximately 26,000 gallons, per day from a single farm. 14 farms of that production profile would supply Hilmar's full daily intake without another farm in the network. Hilmar's actual 400-farm supply network includes operations ranging from smaller dairies producing 20,000 gallons per day to large consolidated operations exceeding 100,000 gallons daily. The geographic distribution of those farms across a roughly 100-mile radius from the plant creates the logistics problem that the coordinated tanker fleet must solve. Collecting milk from 400 dispersed locations on schedules that match farm production cycles, respect the 48-hour quality window that milk freshness requires, and deliver to the plant at the rate the processing equipment can absorb. Hilmar Cheese Company is a dairy farmer-owned cooperative. Yeah, the farms that supply milk to the plant are member owners who receive two forms of value from the cooperative relationship: the milk price paid for each hundredweight of milk delivered, and the equity position that accumulates in the cooperative over time. The cooperative structure aligns the plant's interest in processing efficiency with the farm's interest in maximizing the per hundredweight return from their milk. When the plant operates efficiently and captures the full value of the milk it processes through premium cheese sales and high-value whey protein ingredient revenue, that value flows back to the member farms through the milk price. The 400-farm supply network that Hilmar coordinates operates under a logistics management system that balances multiple competing constraints simultaneously to keep 3 million gallons of milk moving continuously from farms to the processing floor. Each farm has a bulk tank with a defined storage capacity. That tank fills continuously as cows are milked on the farm's schedule, typically twice or 3 times daily. The tank must be emptied before it reaches capacity, which means each farm needs a pickup frequency matched to its production rate and tank size. A farm producing 50,000 gallons per day with a 20,000-gallon tank needs a pickup every 9 to 10 hours. A farm producing 5,000 gallons per day with a 10,000-gallon tank can go 48 hours between pickups. The logistics system must schedule pickup frequency for each of the 400 farms based on their individual production and storage parameters. The tanker fleet that executes these pickups operates as a continuous loop. Drivers running multi-farm routes, returning to the plant, then heading back out on the next route with no meaningful downtime in the collection cycle. At 3 million gallons daily, requiring 430 to 545 tanker loads, the fleet moves at a pace that leaves little slack for delays. A truck that arrives at a farm and finds the bulk tank not ready because a milking was delayed, because equipment malfunctioned, must decide whether to wait or skip that farm and return on the next route. The logistics coordinator managing the network in real time makes that call based on the farm's current tank level, the tanker's route schedule, and the plant's current receiving inventory. GPS tracking on every tanker provides the real-time position data that makes this coordination possible. The coordinator can see every truck's location, estimate arrival times at each remaining stop, identify trucks running behind schedule, and redirect drivers when circumstances require. A truck that completes its route 90 minutes ahead of schedule can be assigned additional stops from another route that is running late, absorbing the delay before it reaches the receiving dock. Temperature monitoring integrated into the GPS system adds a quality dimension to the position tracking. A tanker whose internal temperature rises above the acceptable threshold during transport generates an alert that the coordinator must evaluate. Has the refrigeration unit malfunctioned? Is the load at risk? Does the driver need to divert to the nearest plant or refrigerated holding facility rather than completing the remaining route? At 3 million gallons daily, the quality of every tanker load matters because substandard milk that enters the plant affects the cheese and protein products it produces. The receiving dock, where that 2:14 a.m. our tanker cleared, is the transition point between the farm supply network and the processing plant. And the quality gatekeeping function it performs is the food safety critical control point on which everything downstream depends. Every tanker load undergoes antibiotic residue testing before any milk discharges from the tank into the plant. This is not a sample-based protocol applied to a fraction of loads. Every load, every time. A rapid test that detects the beta-lactam and tetracycline antibiotic classes at concentrations well below the regulatory tolerances, performed in under 5 minutes using the sample drawn when the tanker connected to the dock, must return a negative result before the receiving valve opens. The antibiotic testing requirement exists because commingling has already occurred. A tanker that collected milk from 4 farms carries milk from all 4 in a single unsegregated tank. If one of those 4 farms sent milk from a cow that had been treated with antibiotics and whose milk withdrawal period had not yet cleared, the contamination affects the full 6,500-gallon load. That contaminated load entering the plant would introduce antibiotics into the milk supply at a concentration that, diluted through the full day's processing volume, it might be undetectable in the finished product, but at a level that still violates food safety standards and creates legal liability for the product leaving the plant. The financial consequence of a positive antibiotic test at the receiving dock is immediate and significant. The entire load is rejected and disposed of. 6,500 gallons of milk that cannot enter the food supply. The farms whose milk commingled with the contaminated farm's milk lose the value of their milk in that load. The farm responsible for the contamination faces financial liability for the total rejected volume under Hilmar's supply contract terms. The incident triggers a quality investigation that examines the farm's antibiotic management protocols, treatment records, and milking procedures. On this consequence structure, the liability falling on the responsible farm and the spillover cost falling on the farms whose clean milk mixed with the contaminated milk, creates a powerful incentive for rigorous antibiotic management across all 400 farms in the network. Every farm's milk quality management affects every other farm whose milk ends up in the same tanker. The 3 million gallons that clear the receiving dock each day move through a pasteurization and separation sequence before reaching the cheese-making vats. Pasteurization, heating milk to 161 degrees Fahrenheit for 15 seconds in a continuous high-temperature short-time process, destroys the pathogenic bacteria that raw milk carries while preserving the functional proteins and fat that cheese-making requires. At Hilmar's throughput, the pasteurization equipment processes tens of thousands of gallons per hour in a continuous flow system where milk enters one end, passes through the heat exchanger at precisely controlled temperature and residence time, and exits into the holding and separation equipment on the other side. Standardization follows pasteurization. Cheese-making specifications require milk at defined protein-to-fat ratios that vary by the cheese variety being produced. The standardization equipment adjusts the protein-to-fat ratio of the pasteurized milk by adding or removing cream, the fat fraction separated from whole milk by centrifuge, to hit the target composition for each vat's intended product. Cheddar, Monterey Jack, and mozzarella each have different compositional requirements that the standardization step delivers before the milk enters the vat. The specific gravity and composition of each vat's incoming milk affects every downstream quality variable: the pH development rate, the gel firmness at curd cutting, the moisture content of finished cheese, and ultimately the sensory characteristics and yield efficiency of the product. Standardization consistency is a critical process control step, not an incidental preparation. The cheese-making vats that Hilmar operates at scale are not small vessels. They are large automated stainless steel systems where the biological and chemical transformation of milk into cheese curd occurs under continuous process monitoring. Pasteurized, standardized milk fills a vat to its working volume, tens of thousands of gallons, and the cheese-making sequence begins with starter culture addition. Starter cultures are specific strains of lactic acid bacteria selected for the fermentation characteristics they produce in the target cheese variety. These bacteria acidify the milk by metabolizing lactose into lactic acid, dropping the milk's pH from approximately 6.7 at pasteurization to the target range for cutting, around 6.4 to 6.5 for cheddar. The acidification rate depends on the starter culture's activity, the milk temperature, and the inhibitory effects of any substances in the milk that might slow bacterial growth. The vat's temperature control system maintains the incubation conditions that the starter culture requires. The pH monitoring probe in the vat tracks acidification progress continuously, displaying the curve that the cheesemaker's experience interprets. Too fast means the rennet will be added too early, producing a weak gel. Too slow means the process has fallen behind schedule or the culture is struggling. Rennet addition follows at the pH target. Rennet, the enzyme complex that cleaves the kappa-casein molecule stabilizing the casein micelles in suspension, triggers rapid coagulation. The casein network collapses into a continuous gel as the kappa-casein bridge between micelles dissolves. Within 30 to 40 minutes of rennet addition, the vat holds a smooth, firm gel that will not flow when tilted. The check gel test that experienced cheesemakers use to confirm coagulation completion. The cutting step follows gel firmness confirmation. Automated cutting harps, stainless wire frames stretched with parallel cutting wires, descend through the gel in 2 perpendicular passes, converting the continuous gel mass into uniform cubes. The size of those cubes is the primary determinant of the final cheese's moisture content. Smaller cubes present more surface area through which whey can expel during the subsequent cook and stir step, producing a firmer, lower moisture curd. Cheddar's target moisture is below 39%, which requires a relatively small cut size and extended cooking time to achieve. The cook and stir sequence that follows cutting is where the curd's final moisture content is set. After cutting, the vat's stirring system keeps the curd particles in gentle suspension while the temperature rises under the controlled heating program. Rising temperature causes the curd protein matrix to contract, squeezing out whey through the cut surfaces in a process the dairy science literature calls syneresis. The rate of temperature increase, the final cook temperature, and the stirring duration together determine how much whey expels from the curd before the cooking step ends. The vat's automated control system executes the cook and stir program with the precision that 3 million gallons per day consistency requires. At Hilmar's scale, a cook program that produces cheese at 38.5% moisture on Monday must produce cheese at the same moisture on Friday and on the following Monday. Variability in moisture content across vats and across days affects the aging trajectory, texture, and consumer acceptability of the finished cheese. Process consistency is not only a quality aspiration, it is the operational requirement for supplying retail and food service customers at scale. After cooking, the whey curd mixture drains from the vat. At Hilmar, the drainage systems that separate curd from whey at this point in the process move enormous volumes. Approximately 90% of the incoming milk exits as whey at the drainage step. Of the 25 million pounds of milk entering the plant daily, roughly 22.5 million pounds leaves as whey liquid. The 2.5 million pounds that remains as curd will become the 1 million plus pounds of cheese produced after pressing and moisture loss. That 22.5 million pounds of daily whey volume is not waste. It is the raw material for Hilmar's whey protein business, a revenue stream that fundamentally changes the economics of cheese production at this scale. Whey protein's transformation from a disposal problem into a premium ingredient represents one of the significant value chain developments in the global food industry over the past 40 years. Before the sports nutrition market developed commercial scale in the 1970s and 1980s, and a liquid whey from cheese plants represented a volume management challenge. Early industrial cheese operations disposed of whey by spreading it on fields, feeding it to livestock on adjacent farms, or paying for wastewater treatment. The protein and lactose it contained had limited market outlets. Processing it into useful ingredients required capital investment that the ingredient prices of the era couldn't justify. The whey protein concentrate and isolate market that grew from the sports nutrition industry's demand for high-quality protein changed this calculation completely. Whey protein's amino acid profile, rich in branched-chain amino acids, leucine in particular, that have specific biological roles in muscle protein synthesis, made it the preferred protein source for the dietary supplement formulations that the sports nutrition market built its products around. Demand for whey protein concentrate and isolate grew faster than the dairy industry's capacity to supply it through the 1990s and 2000s, driving ingredient prices to levels that justified the processing investment. The infant formula industry provided a second major demand driver. Whey proteins, specifically the alpha-lactalbumin fraction, are critical components of infant formula designed to more closely approximate the protein composition of human breast milk. Formula manufacturers require consistent, traceable, high-quality whey protein ingredients at volumes that only large-scale whey processors can supply. Hilmar's position within this market, processing 22.5 million pounds of whey daily from 3 million gallons of incoming milk, makes it one of the largest single-site whey protein producers in the world. And the whey protein concentrate and isolate products leaving the Hilmar facility reach food manufacturers on 6 continents, infant formula producers in Asia, sports nutrition companies in Europe, dairy ingredient manufacturers in South America. The whey processing sequence at Hilmar runs as a parallel operation to the cheese-making line, not a secondary process, but a co-equal production system processing an ingredient stream as large by volume as any industrial food operation in the country. A fresh whey arriving from the cheese vat drainage systems enters a clarification step that removes fine curd particles that pass through the drainage equipment, particles that would interfere with membrane filtration performance if left in the stream. Clarified whey moves to ultrafiltration membranes, hollow fiber or spiral wound membrane elements that allow water, lactose, and small minerals to pass through while retaining the whey proteins. The ultrafiltration process concentrates the protein fraction from approximately 0.6% in fresh whey to 35 to 80% on a dry matter basis in the retentate, the fraction retained by the membrane. Whey protein concentrate products with 34, 50, and 80% protein content correspond to different levels of concentration and different processing depths, each with different applications and price points in the ingredient market. Whey protein isolate, the highest protein form, did above 90% protein on a dry matter basis, requires an additional ion exchange or diafiltration step beyond standard ultrafiltration to remove the remaining lactose and fat that keep WPC 80 below the isolate specification. The additional processing adds cost but produces a product that commands the highest per-pound price in the whey protein ingredient market, particularly for the infant formula and clinical nutrition applications that require minimum fat and lactose content. After concentration, the whey protein stream moves to evaporation equipment that reduces the water content further before spray drying. The spray dryer, a large cylindrical vessel where the concentrated protein solution atomizes into fine droplets that dry instantly in a hot air stream, converts the liquid concentrate to the powder form that shelf stability and international shipping require. Powder products that leave Hilmar's spray drying towers in bags or bulk containers may travel to customers in Southeast Asia, the Middle East, or Europe, where the cold chain limitations of liquid dairy ingredients do not apply. Lactose, the sugar fraction that passes through the ultrafiltration membrane in the whey permeate stream, undergoes its own recovery and processing sequence at Hilmar. Pharmaceutical-grade lactose, food-grade lactose, used as a carrier ingredient in dry blending, and animal feed-grade products emerge from different processing depths of the permeate stream, each capturing value from a fraction that earlier cheese operations disposed of. The automation that Hilmar has invested in across the cheese-making and packaging operations allows the plant to run 1 million pounds per day output with a workforce that the same production volume would have required at multiples larger in earlier processing technology eras. The robotic packaging systems that handle finished cheese blocks, weighing, labeling, casing, and palletizing, execute these steps with precision and speed that manual operations at this throughput could not match. A robotic palletizer stacking 40-pound cheese blocks in precisely organized cases onto pallets operates continuously without fatigue, producing consistent stack patterns that maximize storage density in the refrigerated warehouse and reduce the handling damage that irregular manual stacking creates. The process control systems that manage vat temperatures, pH curves, cook programs, and membrane filtration performance generate continuous data streams that the plant's quality and production management teams use to identify deviations before they become product quality problems. A vat whose pH curve is developing 15 minutes slower than normal alerts the cheesemaker to investigate. Is the starter culture encountering an inhibitor? Is the temperature controller underperforming? Rather than discovering the problem when the finished cheese fails the quality specification. 24/7 continuous operation creates a maintenance challenge that the plant manages through preventive programs timed to avoid disruptions during peak production periods. Equipment scheduled for preventive maintenance comes offline during windows when the production schedule has built sufficient inventory to absorb the reduced throughput. Unplanned equipment failures at 3 million gallons daily throughput are expensive. Milk backed up in tankers waiting for receiving capacity, or curd held past optimal timing in vats waiting for drainage equipment, which makes the preventive maintenance investment clearly justified. 3 million gallons per day, 1 million pounds of product. The tanker that cleared the dock at 2:14 in the morning is already halfway back through its second route. The milk it delivered an hour ago passed through pasteurization, entered a vat with starter culture added at 2:47 a.m., and now sits at 99 degrees Fahrenheit, acidifying toward the rennet addition point. Rennet will be added at approximately 4:15 a.m. By 6:30 a.m., when the day shift arrives, that vat's curd will drain and press. By tomorrow morning, it will be cheese. Across the same plant floor, the whey from yesterday's vats is moving through ultrafiltration membranes, concentrating toward the evaporators, approaching the spray-drying towers. By afternoon, it will be powder in a bag, ready to ship to a food manufacturer whose formula depends on the consistent protein specification that Hilmar's processing delivers. Hilmar Cheese Company began as a farmer-owned cooperative solving a specific regional problem. San Joaquin Valley dairy farms needed a processing outlet that could absorb the milk their scale of production generated and pay a price that reflected the genuine value of that milk. The cooperative's member farmers built the processing capacity to convert milk into cheese and protein products that captured more of the chain's total value than raw milk sales could command. What they built, over 3 decades of expansion, became the largest single-site cheese manufacturing operation in California. The 400 farms connected to it by the tanker fleet and the quality testing infrastructure don't individually determine what happens to the milk once it leaves their bulk tanks. But the cooperative structure ensures that what happens to that milk, the prices the cheese commands, the protein premiums the ingredient market pays, the operational efficiency that continuous processing at this scale achieves, flows back to the farms as the economic return for the milk they delivered. At 2:14 in the morning, another tanker clears the dock. The vats are filling, The cultures are working, the whey is concentrating, the spray towers are running, the system doesn't stop. If this deep look at how 3 million gallons of San Joaquin Valley milk converts into cheese and global protein ingredients every single day gave you a clearer picture of the industrial dairy processing system behind everyday food, hit the like button and help more viewers find this kind of detailed content. Subscribe for more stories that go inside the supply chains, processing systems, and cooperative structures behind the food products most people never think twice about. Drop a comment and tell us where you're watching from. These stories reach places we don't always anticipate, and every location in these comments matters to us.